So thank you very much for the invitation, and thank you very much for the introduction and for the opportunity to give this talk. So first of all, disclaimer, this is not my research line. It's a very small part. I do some other crazy hyper-technical stuff. So I chose something not too technical, which makes me not that expert on what I'm going to tell. But I still have some work on the subject. But it's called Panoramic talk. So I mean, I wanted to do something that is not too technical, and the main line of my research is extremely technical. So I try to go in some other direction. Most of this, or almost everything I've done in this, is with Pedro Montero, who's sitting there, and Roberto Villaflor, who's not here, and Victor Gonzalez, who's also not here. But they are all from Chile. OK, so very simple first slide. So projective space, you all know what it is, but let me just show you because I have a nice picture for it. So you take a vector space. I will need the dimension of it at some point. So it's vector space of dimension n plus 2, so that you get a projective space of dimension n plus 1. And the definition, I will not read it. You know what it is. But the important part, I'm taking, you remember the title, no? Hypersurfaces. So I'm going to take hypersurfaces in projective space. I want them to have dimension n, so I take n plus 1 dimensional projective space and n plus 2 dimensional vector space to create it. And a projective hypersurface is what you know. You just take one polynomial. So first of all, wait, sorry. I forgot to put this on. Don't bother me. No, I don't find the, here's the airplane. OK, so a homogeneous form of degree d is just an element in the symmetric product. We don't care. But we take a basis somewhere. We take a basis for the vector space that is going to be called, or for the dual, just for everything to make sense, it's going to be called x0 to xn plus 1. So this is my choice of variables for polynomials. Again, it's not that standard. I have n plus 2 variables. They are called from 0 to n plus 1, again, to have them agree with the dimension of projective space for the variety to have dimension n. And then, if we take a homogeneous form of degree d, which is just a polynomial of degree d in this set of variables, a projective hypersurface of dimension n and degree d in this projective space given by the vector space B of dimension n plus 1 is just the set of zeros of this polynomial here. So this is the object we're going to be studying. Very simple, probably the simplest version of algebraic variety you can imagine, compact. So there are two very famous examples that will appear through the talk at different points. So the first one is the Fermat hypersurface of dimension n and degree d, which is going to be given by this equation. So each of the variables to the power d, the sum of all of them, coefficients 1 everywhere. And apparently, according to Wikipedia, this is a two-dimensional cross-section of the Fermat quintic threefold. So threefold means dimension 3. Quintic means d is equal to 5. And of course, if it's three-dimensional, I cannot draw it. Yeah? I cannot draw it in three-dimensional space, so you have to cut it somehow. And apparently, this is one of the cross-sections, two-dimensional cross-section of that. Again, I didn't do the picture. I took it from Wikipedia, which is common, how is it called? I don't know, free to use. I checked. It's Creative Commons, yes, Creative Commons license. So again, another hypersurface. So Klein hypersurface, which is supposed to say Klein there. So the Klein hypersurface of dimension n and degree d is given by, now the second simplest form you could imagine is just take every variable. Instead of putting them to degree d, you put them to degree d minus 1. You're still missing 1 degree, so you put the next one. X0 to the power d minus 1, x1, and so on until the end you get to xn plus 1, d minus 1. Then you're missing one variable, so you use the first one. So this is Klein hypersurface because Klein studied one of these. And again, this picture, this is Lefschetz cubic surface, which is isomorphic to Klein cubic hypersurface. Surface. Sorry. So this is a picture, again, stolen from Wikipedia in Creative Commons. I don't know the name. License, Creative Commons license. Great. So an algebraic variety is smooth. You all know the definition, but I I used to have a very simple definition. Now I wrote the real one. So an algebraic variety is smooth at a point if the dimension of the tangent space at set point is equal to the dimension of the variety, and it's called smooth if it's smooth at every point. And the set of points where it's not smooth are called singular, and there you have a picture. One which is smooth because it looks, looks like there are no sharp points, and this one is clearly not smooth because there are some sharp points in the picture. Good. So this is just very general starting point. The criterion to decide if a hypersurface is smooth, I think everything is, so every variety for me is irreducible, so the polynomial is irreducible that it gives. So there is the Jacobian criterion that works very, very simply. It says if you want to know that your variety, if a point is singular, then all derivatives should vanish. This you probably learned the second lecture in algebraic geometry. And this very, very, very simple criterion we can already use for something when it's hypersurfaces. Okay, not yet. We will use it later. So there's the first result that is the basis of everything I will be doing is the following result by Matsumura and Monsky, in very old one in '64, which says the following. If you have two smooth hypersurfaces of dimension n greater or equal than 1 and degree greater or equal than 3, degree 2 is complicated. They are quadratic forms, so everything is different. So they are in the complex projective space Pn plus 1, and you have an isomorphism between x and y, then the isomorphism between x and y came from isomorphism from projective space, so automorphism from projective space, with the only exception of 1, 3 and 2, 4 for n and d. So every automorphism of x is linear. Linear means it comes from the ambient space, projective space, and it's also a finite group. This you have to prove, but it's part of their paper, and they prove it in different statements. So the cases that are excluded here are really exclusions, because if nd equal 1, 3, this is an elliptic curve whose automorphism group is not finite, because it contains the curve at least, maybe some more. And if nd is 2, 4, is a K3 surface, which not all the time, but in many cases have an infinite automorphism group, and both in many cases have nonlinear automorphisms. So the exclusions are really excluded. It's not because they couldn't prove it. Great. And now the automorphism group of projective space, you probably also know it, but I just give you the context. So it's PGL of the vector space that defines the projective space. So in our case, it's PGL n plus 2 over the complex numbers. I haven't said that, but everything is over the complex number. It's not really necessary. Probably algebraically close is enough for most of it, but I like complex numbers. So if you take an automorphism, it has to take O of 1, which is a generator of the Picard group, into another generator of it. So it could be plus or minus 1, O of plus minus 1, and one of them has no sections, the other half, so it has to take it to O of 1. So every automorphism of P1 and plus 1 has to come from an automorphism of B, which is GLB. So that's the word linear in the previous slides. So every automorphism of projective space is linear, meaning that comes from the GL, that V, where V is the vector space that defines projective space. And so it's given by a matrix. So you just take x0 until xn1, and you send it to multiplication by a matrix. The vector is not in the right direction. No, it should be transposed, but it looks awful. So just imagine that all vectors are in the right direction so that multiplication can actually happen. Yeah, so m times x is not really multiplicable the way it is. And if you want to obtain the identity, okay, the matrix you multiply by your vector has to give you not exactly identity, but you can have it multiplied by a lambda. And so the matrix M has to be a multiple of the identity. So that's how you get PGL instead of GL up there. But the important part here is automorphisms of Pn come from matrices, and automorphism of hypersurface, if you exclude 1, 3 and 2, 4 as dimension and degree, they come from matrices. So you can work with matrices, and you can do all the linear algebra you want for these algebraic objects. Okay, so let's first take another. Also, you know it's finite, the automorphism group, so every automorphism has finite order. Take one automorphism. Okay, the order is finite. I will call it P because it will be prime very soon. We can always choose a matrix that diagonalizes it. So we can assume, up to changing the coordinates in the projective space, so the x0 until xn plus 1 that I've chosen, that the automorphism is given by something like this. So it's not said, but psi is a p root of unity, and then you have to send x0 to a p root of unity with some, so you take one primitive, which is psi, and you take some exponent, and those exponents can live between 0 and p minus 1. So this is the elements that encode all possible automorphisms of a hypersurface, because it's all possible automorphisms of Pn of order P, or divisible by a divisor of P for the moment. Okay, so we can put everything diagonal. And now we have to, the Jacobian criterion I showed before, I should have put it right here. I reorganized the slides and destroyed it. So if you take a hypersurface of dimension n and degree d that is given by some polynomial, and actually in the polynomial one of the variables appears with degree different from d or d minus 1, then the thing is already singular, and it's just computing it. I put it because it's very ridiculously simple. Yeah, you take a polynomial that has degree at most d minus 2 in the variable x0, and then you compute, and you find that you compute Jacobian criterion, and you find that the point where you put the 1 in the variable, so x0, and 0 everywhere, has to be singular. So it's a very simple verification with Jacobian criterion, and I'm going to use this to prove something. That's what I really like to tell this story, because it's probably, I'm telling you, it's probably the second lecture in algebraic geometry you have, and you can use it to prove something. Okay, so let me try to walk you through the proof. Take an automorphism of a hypersurface of dimension n and degree d, where n, d is not 1, 3, nor 2, 4, so it's given by a matrix. And since it's an automorphism of the degree of the hypersurface, it has to send the polynomial defining the hypersurface into the polynomial, but maybe not the whole the exact polynomial, it may be a multiple. Yeah? We are not proving anything yet, but we're going to, actually, I can show you what we're going to prove, but you're spoiling the future. So we're going to prove that an automorphism of order prime has some very particular shape. Yes? But I wanted to walk you through the other way around. So as I said, the polynomial given the hypersurface has to be sent to the polynomial maybe times a multiple. But let me assume for a moment, I will not show you how to get rid of it, but believe me, you can. I will not show you any other proof later, so just believe me for this small part, that assume first that you send the polynomial to exactly the polynomial, not a multiple of the polynomial. Okay. We know that the form in every degree, so the polynomial in every degree has to be either x0 to the power d or x0 to the power d minus 1, x1, because otherwise it would be singular by the previous lemma. So assume first that it starts with x0 to the power d. Okay, you apply your automorphism, you will get some psi, it's here. You apply your automorphism, you get some psi to the d times sigma 0. And you obtain that this has to be 1, so p divides d. Very simple. That's one option. The polynomial could divide d. Then the other possibility is the form starts with x0 to the d minus 1, x1. And now you have two options. Because okay, here's the application of the automorphism. So you you take d minus 1 times the coefficient in the 0 variable plus 1 times the coefficient in the 1 variable. So this is what it is. This has to be 1 again. And there are two options. Either p divides d minus 1 and x1 is 0 for that to be 1, or no one gets to be 0. And then you have like an equation, mod p, involving x0 and x1. Right? And then you can extract x1 as a function of x0 mod p. And if this happens all the time, you can iterate the process. So you have either p divides d minus 1, or this. And you can turn this into a theorem, which is the one I have here. So you take n, d, and p positive integers with, again, as before, n bigger or equal than 1, d bigger or equal than 3. You exclude 1, 3, and 2, 4, and p prime. Then p is the order of a smooth hypersurface of dimension n and degree d, if and only if p divides d minus 1, or exactly the other possibility was, if you iterate and look at what you get at the end, is 1 minus d to the... Oh, of an automorphism, yes. The word automorphism is missing, sorry. So P is the order of an automorphism of a smooth hypersurface of dimension n and degree d, if and only if P divides d minus 1, or this. So 1 minus d to the power L is equivalent to 1 mod P for some L in between 1 and n plus 2. So this is exactly the other option, the iteration in the previous slide. Really, only Jacobian criterion, you can prove some theorem. I did this for my master degree. I'm not that young. It was 2005. But then I went on PhD and I forgot about it. And then after PhD, I said to my professor, okay, maybe we should write this down. And then we wrote it down 8 years afterwards. And that's it. And then it was completely forgotten. We wrote maybe 2 papers. There's another thing before, but forget about it. It was completely forgotten in life. Okay, now we did some other thing that we're going to be using in the future. So there is, so you can, okay, now you know automorphisms of prime order. You can ask yourself 2 questions now. When is the automorphism group the largest, or when is the automorphism itself the largest order? Yes, there are 2 natural questions. I will talk a little bit about both of them. So the first, we asked it immediately. So at the same time, if you have, and now for some reason, for some technical reason, for the statement to be simpler, I ask n greater or equal than 3 now, but a different statement works for n equal 1 and 2. So d greater or equal than 3 as all the time, and p a prime number. So from the previous criterion, you can derive yourself a bound for the order of an automorphism of prime order, which is this number. So it's 1 minus d to the power n plus 2 is what was written there, and this is divisible by d. So you divide by d, and then the prime number has to divide the other part. And of course, the other part could be prime. And if the other part could be prime, and is prime sometimes, this is the biggest prime number that can be the order of an automorphism of a smooth hypersurface of degree n, of dimension n and degree d. So that is the number. And in that case, the hypersurface has to be the Klein hypersurface, and n plus 2 has to be prime. It's not if and only if, it's just in one direction. If it were if and only if, it would be a generator of prime numbers, no? Which is impossible. And actually, these kind of prime numbers are called backstaff primes. So we call this, it's conjectural that there are infinite number of them. But like all these conjectures, is unprovable, but probably true. There are probably infinite primes like this, infinite cases where Klein hypersurface has a prime of this order, and in that case, n plus 2 has to be prime. And so we call it Klein hypersurface of backstaff type. Actually, that name came last year or 2 years ago. Okay, so this solves how big can one automorphism be. And then we really forgot about it. Now it's true. And then Pedro Montero had a master thesis himself. So his master thesis was read the master thesis of the previous guy and do something. And I happen to be the previous guy. You can tell he's 10 years younger than me. So we started doing something different, but for some particular reason, we needed to generalize the criterion before. I forgot what time did I start it. So 30? Yeah, 30, okay. It's okay, just, I hate to be over time. So for some particular reason, we had to generalize that. I will tell you why later, but we had to generalize the previous criterion. So again, with Victor Gonzalez, and this time with Pedro Montero, who was too young to participate the first time. He was probably in school. We generalized, no, not probably, in all likelihood, in all likelihood, he was at school unless he's really, really gifted. So we had to generalize not for p, but p to the power r, and not just saying, okay, p divides d, but just precisely how much. And we came up with this criterion. I will not read it. It's just as before. I mean, the important part is we use the same technique, stupid Jacobian criterion straightly applied, and we obtain this classification for whenever p to the power r is the order of an automorphism of a smooth hypersurface of dimension n and degree d. If, well, okay, if p divides d minus 1, this numerical stuff has to happen. If p divides d, then this numerical stuff has to happen. And if p does not divide either one, it's the same numerical condition as before. Okay. We were doing something different. And as it happens very often in this subject, for no particular reason, after 10 years of no one doing, maybe mostly no one doing nothing, someone appeared at the very same time with the same result that us, doing something different. He wasn't doing this. We were not doing this either. But actually, at the same time, he put it on the archive, so we had to hurry up to finish it. And we finished it like in 3 days, maybe, and put it on the archive. Again, we had some bigger goal, and he had some other bigger goal, but we had this big intersection in the middle. He actually computed for all numbers, not just powers of primes, which we could have done, but look, the awful answer. So I just put it how awful the answer is. So we didn't have the courage to even try, but again, this guy had. Yeah, he needed it. Probably he wouldn't have done it hadn't he needed it for another purpose. So you can actually tell if n and d, again, as all the time, n greater or equal than 1, d greater or equal than 3. So a q now is any natural number. So then q is the order of an automorphism of a smooth hypersurface of dimension n and degree d, if and only if q is a factor of one of these numbers. So the first one is ours, you see? And then you have all the other possible cases that we weren't strong enough to try. Okay, so let me now give you, remember the Fermat hypersurface? It was given there. I will, if I still have time by the end, I will actually prove that this is the automorphism group of Fermat hypersurface. Okay, the automorphism group of Fermat hypersurface, whenever n is not 1, 3, and 2, 4, is this. And this is very obvious, no? There is Sn plus 1, which is the permutation of the variables. This looks pretty symmetrical in the variables. And there is z over dz to the power n plus 1. You can put d root of unity anywhere in front of each variable, no? And then, since you are projective, one of them dies by the projective equivalence. So this group clearly acts on X, and it happens to be the whole automorphism. And this conjecture down here is folklore conjecture. Let X be a hypersurface of degree d in Pn. Then, up to a few low-dimensional and low-degree exceptions, Fermat is the one that realizes the biggest possible automorphism group. I don't know how folklore it is, but Pedro told me it was folklore. We actually stated in a paper that just appeared this year. And we were thinking maybe we should try to prove something like this someday, but then thankfully we never tried. Because a few months ago, again, two groups, again, one appeared. So the Chinese named people, everything, mostly everyone is Chinese named. But so the Zhang, Yu, and Zhu published something on the archive with this theorem, and 3 or 4 days later, Esser and Li appeared with the same, but this time it was the exact same result. I mean, they were aiming to prove this, and they all proved it, sadly. And we really thought about trying it. Maybe we would have been halfway through proving it when they appeared, so thankfully we didn't. So the theorem is the following. So the conjecture before is no longer a conjecture. So let X be a smooth hypersurface of degree d and in Pn plus 1, where d is degree greater or equal than 3, and you exclude the cases you have to exclude. Then the automorphism group, the order of the automorphism group is at most the order of the automorphism group of Fermat, which was, of course, n plus 2 factorial times d to the n plus 1. And there are these exceptions. So there are only 6 exceptions which are here. And they are all realized by exactly only one hypersurface. They give the hypersurface. Okay, each of these bound is sharp, and the hypersurface achieving this bound is unique for every pair. So for the first one is Fermat, and for the other ones, they give the formulas. They are not so nice to look. I stole this one from Esser and Lee. So it's the... Sorry? Yes, the one is Klein for 1,4. The others are crazy. Most of them are crazy. So Pedro's, which is the name for 1,6? Women 6, yeah, he just told me the name. The others are just crazy with some crazy numbers in the middle. We were aware of some of the exceptions, not all of them. We would have never expected to be that many. So I stole this. This is the exact statement from Esser and Lee, and I stole this table from the other group. So this is the group that realized the automorphism. Okay, so the two problems of finding the largest possible automorphism and the largest possible automorphism group are already solved by these different works by several people. So let me move on to something new. You see, the same people, the same year, this is what we were doing. So when we intersect with Zeng, we were not trying to do that, we were trying to do this. So now, okay, everything is wrong in these slides. So this is, of course, is GL to PGL. Yes, it's the projection from GLB to PGLB. And we say, let G be a subgroup of the automorphism group of a hypersurface, which is, of course, a subgroup of PGL, and X is a hypersurface. We say that G is liftable if there exists a group in GLB that projects to G, and for every element in this G, F is not sent to a multiple of F, but it's sent to exactly F. So in this case, we call the automorphism group liftable. That means that actually there is, instead of being a group in PGL that fixes the hypersurfaces, there is a group in GL that fixes the form, the whole form. And just wait, I say it later. And then what we wanted to prove is exactly the statement here. So let n be greater or equal than 1, d be greater or equal than 3, with the excluding cases, 1, 3, and 2, 4. Then the automorphism group of every smooth hypersurface of dimension n and degree d in P n plus 1 so is liftable if and only if d and n plus 2 are relatively prime. So in that particular case, everything is liftable, and in the other case, it's not. We can exhibit non-liftable automorphisms. And the non-liftable automorphisms have to divide d and n plus 2. So this theorem was inspired by papers by Ogiso and his co-authors that actually I will name them later on. And Ogiso is the one that actually brought the subject back into life. So it was completely dead after we did it, and he brought it back. So now let me come to the Klein hypersurface. We want to compute the automorphism group of Klein now. So the Klein was this equation, so we saw it before. And this number that have appeared many times, let me call it m now. So 1 minus d to the power n divided by d. So regardless of whether this is or not a prime number, X admits an automorphism of that order, which is just putting, so it's just written here. So you just take a dm root of unity, and you go put the numbers 1, 1 minus d, and so on. And if you compute, it closes up the way it should. And of course, you also have the automorphism that shifts variables by 1. Yeah? Send x0 to x1, x1 to x2, and so on. With these two automorphisms, you can create yourself an action on the Klein hypersurface of this group. Yeah, we are seeing it. We proved recently, actually, the following. So if you have n greater or equal than 1, d greater or equal than 3, and the Klein hypersurface, then the automorphism group is what you have here. So only the red parts are what we proved. Everything else was already proven. So again, the first one is an elliptic curve. So you have to compute some invariant to know what to put here on the right. It happens to be z over 6z. The next one is Klein. This is what Klein did, actually. And the others were known. I don't remember. Haru probably here. I'm not so good on names. And 2 times 4, we don't know. Apparently, no one knows. If you know what you put there, please tell us. So this is the K3 case. We have asked all the experts in K3 surfaces. We know it's infinite. So actually, Michela probably somewhere told us, explained us how this is infinite, but we don't know what the group is. And okay, this PSL2F11, this is Adler by the end of the last millennium. And this. Okay, and in the last minutes, I would like to give you an idea of how we prove this, because again, it's something very simple, very standard, and it allows you to prove stuff. So I kind of like the idea of not using big machinery, but actually proving things. Again, so it's not in the archive anymore, it's published. I stole these slides from a previous talk. So first remark that in this automorphism here, so sigma was diagonal, yeah, was acting on each variable, and the other one, the n plus 2, is just shifting by 1. So in all cases, the matrices giving these automorphisms, they have at most one coefficient that is different from 0 in each row and each column. Yeah, one is just shifting with coefficients 1, and the other one is diagonal with some roots of unity in the diagonal. So based on this, we are going to call a matrix a generalized permutation matrix if there exists at most one coefficient different from 0 in each row and each column. And we're going to call a matrix a generalized triangular matrices if, okay, the thing before was the same as taking a diagonal matrix and multiply by permutation matrices on both sides. So a generalized triangular matrix is the same, but you put in the middle a triangular matrix. So these are going to appear in the results very soon. So here, to compute the automorphism group of X in the remaining cases that the ones I showed in red, we actually use something that is or was called the differential method, probably by Ogiso and Yu. They claim it was originally by Poonen in a paper from 2005. And actually, Ogiso and Yu, they use it to compute all the automorphism groups of all smooth quintic trefoils. So they give a full list of what that can be. And they bring it to a set of equations. Okay, here is the equations. And they use some very, that's artisanal, exists, some very handmade technique to prove the automorphism group of each one of them, to actually go and compute. And then, again, the same Yu and Vi, or Y, I don't know, they compute all the automorphism groups of all smooth cubic trefoils. And they do the same thing. They start with some big machinery, they reduce it to a set of equations that all the automorphism groups are in this set of hypersurfaces, and they compute the automorphism group of each and every one of them by hand, very by hand. So, and they in every single case, they use this that they call the differential method. But they use it for each and every one of the equations. So we said, okay, there must be something more general. And we try to generalize this. So this is what I'm going to tell you in the following minutes. So again, we come back as before. Don't forget, the vector space is n plus 2 dimensional. The variables are x0 to xn plus 1. And the polynomials are complex polynomials in these variables. And we have one polynomial that is homogeneous in n plus 2 variables of degree d. Okay, so the directional derivative operator, so the directional derivative from calculus, you just take your polynomial. So you pick a direction and a polynomial, and you derive your polynomial with respect to that direction. Very simple. So normally you use this by fixing the direction. No? If you fix the direction x, you have some partial derivatives for some particular choices of x and so. But here we're going to fix the form. So you fix the form and you apply the directional derivative in all directions while you fix the form. And we define the differential rank of this form exactly as the rank of this map, so the dimension of the image. So you take your form, you take all possible directional derivatives of it, and you compute the image of, you take the span of it, and you compute the image, the dimension of the image, and you call that the differential rank. So the differential method as they call it. It's a theorem that you prove in one line, that you could give your calculus students to prove. And it's the following. So if X is a hypersurface of dimension blah, blah, and so on, then for every, now if you fix one direction, now you take the form. So this is the form giving you a smooth is missing, but a smooth hypersurface. Yeah, and you pass it by an automorphism of the smooth of the hypersurface, then this differential rank of the derivation of f with respect to one direction has to be the same as the derivation of f with respect to the image of that direction by the automorphism. So in general, all of these will have dimension n plus 2 in general for a general polynomial. But if your polynomial is very special, the differential rank in some direction may be really small. So for instance, we are going to see the example of Fermat. So the differential method, as I said, for a general polynomial says strictly nothing. Yeah, because on both sides you will have just n plus 2. But if you have a very special polynomial that you have something smaller, this gives you a constraint of the shape of the right side. And that will give you a constraint on the automorphism. And that's the way they use it in several particular examples, and we kind of formalize this into a theorem that does not contain all their cases. So you can do more with the differential method case by case, but you can do lots of them at once. So yes, now I come back to Fermat hypersurface, and let me show the way the differential method works in that particular. This is known. I mean, this is not some new result. It's very well known from a long time. But the method of proof is very direct. So let's take Fermat hypersurface. You have it here. And you take an automorphism of Fermat hypersurface. So here we're going to choose as direction the partial derivatives. So the partial derivative of f with respect to one direction, the differential rank of that, okay, when you derive with respect to xi, you just get xi to the power d minus 1 with some constant that no one cares. And the differential rank of that is 1. Because if you take differentiation with respect to any variable, it gives you 0, except with the variable xi. So you have dimension 1. Instead of n plus 2, so you have a very small differential rank. You have the hope that you can do lots of things with this. So now you know that the differential rank of this has to be 1, because you prove it to be 1 up there. But here, the differential rank is very easy to compute. So if your automorphism is given by the matrix phi ij, then the differential rank is computing the differential rank of that formula there. And of course, the only way that that is going to be 1 is if only one of the variables appear. That means that all the coefficients in that sum have to be 0 except at most one of them. So, as I said before, this I call a generalized permutation matrix. So, using this ridiculous computation, and believe me, the proof of the differential method, it's also one line. To be true, it's actually 2 lines in the paper. It really is. In the archive version, at least, I don't know the final. So you can prove that the automorphism group of this hypersurface that could have been really complicated, it has to be generalized permutation matrix. And once you know it's a matrix with lots of zeros and very few numbers, you can compute like a crazy guy. You just go and compute and see what has to come out. And actually, I'm not showing you that part, but you go and compute, and actually, this is the only thing that can come out. So if your hypersurface is given by an equation with very few monomials, and you have some luck, you may be able to use this to prove or to compute the full automorphism group, to prove that they are given by some generalized permutation matrices, and then compute the whole automorphism group. So let me give you the way you have to, okay, the way we found to formalize this into a theorem. Again, we take a polynomial, and we're going to define the distance between monomials. And the distance between monomials is exactly what you expect. So the difference of the exponents in each variable, and then you have several of them, so you sum over all of them. So it's here. Since the polynomials are homogeneous, this is always a multiple of 2, because they're going to compensate by being homogeneous. If they were not homogeneous, this could be not a power of 2. And then we define something Actually, we couldn't came up with a better name. Don't tell me if you get a better one, because it's published already. So we call the sparsity, the sparsity of f, exactly the minimum distance between monomials in the equation. So how close the monomials are. The minimum could be 2, but sometimes it could be bigger. So for Fermat, maybe I should say that. So for Fermat, the distance between two of these is 2d, yeah? Because x0 minus x0 here appears with power 0, so it gives you d. The other one gives you minus d, so d plus d is 2, and you get that so the sparsity of Fermat is 2d. And we define the variables of f exactly as the variables that appear. So it's an equation, some variables appear, some variables may not appear. So the number of variables, the set of variables that actually appear in one form, we define it as the variables of it. Let me show the whole thing. So we're going to, maybe not, we're going to define a relationship between variables in forms. We say that xi is less than equal than xj if the variables that appear when I derive f with respect to xi are a subset of the variables of f when I derive with respect to xj. So this defines a relation which may or may not be an ordered relationship, despite the notation I used. So here's an example where it is not an ordered relationship. So if I take this form, yeah, okay, when I take x0, so the variables that survive when I derive with respect to x0 is x1 here, x1 here, and x0 here. Those are the variables that survive. And when I take derivative with respect to x1, the variables that survive are the same. So we have x0 less or equal than x1. Okay, it should be strict, no? x1 strict less than x0, so they have the same. It's not a strict order. And in the other case, if we have the Fermat equation, then nothing is comparable, because the set of variables that appear when I derive with respect to x0 is again x0, and so on. Sorry? Yes, it's the trivial poset, but it is. Yes? It's the trivial poset, but it is a poset. And actually, the theorem that you can prove with these notions is the following. So again, you take one hypersurface of dimension n and degree d with n greater than 1, d greater or equal than 3, and nd not 1, 3, or 2, 4. So if the sparsity, so the minimum distance between monomials, which in general is 2, but if it happens to be greater than 4, so starting from 6, and this relationship we defined before happens to be an order, then the automorphism group of X is actually composed only by triangular matrices, by generalized triangular matrices. And even stronger, if the poset is trivial, as it happened in the case of Fermat, you're not going to be given just by triangular matrices, generalized triangular matrices, by generalized permutation matrices. So this is a theorem that explains why in Fermat we could prove it. And if the hypersurface is interesting, it's very likely falls in this category. Because, just a general polynomial will give you a very uninteresting hypersurface. So if your hypersurface has some interesting behavior, probably falls in the conditions of this corollary. And so, actually, as I said before, this proves essentially all the examples with some very few exceptions made by Ogiso and Yu, and then Yu and Bai and Yu. And in particular, it proves our case. So I told you we wanted to prove the result for the Klein hypersurface. So let me give you in the last minutes the corollary. So the automorphism group of the Klein hypersurface is what I predicted it to be in our cases when n is greater or equal than 2 and the degree is greater or equal than 4. Is given exactly by this, and this is the proof. So in this case, you can go and check, because d is greater or equal than 4, then this d minus 1 is 3, so the distance between two consecutive monomials is 6. So the sparsity is going to be greater than 4 because it's at least 6. And the variables that appear are these. So whenever you try to compare xa and xj, you get that they have to be the same. So the thing is a poset. And it's actually trivial poset. So you obtain that the automorphism group has to be given by a generalized permutation matrix, which is what we wanted to use the theorem I showed before. And now that you have that they are generalized permutation matrices, you just go and compute. And actually, I put the computation. So you have the equation, yes? And of course, if you're going to put some matrix here, yeah, the only possibility is that x0 has to go, say, to x1. But then once the x0 goes to something times x1, you're forced that x1 has to go to x2 and so on, yeah, by the shape of the equation. So it has to be of this shape. Once x0 goes to x1, then x1 has to go to x2 and so on. And then you can have multiples of that. So x1 goes to x2, but then you're fixed that x1 has to go to x3 and so on. So you have immediately that this is the way it has to be. And of course, you have, if you take all the coefficients equal to 1, you have the cyclic permutation that I showed you before. So you can use that cyclic permutation that has order n plus 2 to get it to be diagonal. And once you put it to be diagonal, then we can change the representative of the automorphism to make sure that, I don't know, the coefficient 0, 0, and the 1, 1, which is the one that's going to appear in front of the first monomial, is 1. That changing the representative. And so you obtain, by just applying to the next step, to the next monomial, that this has to be 1. And so you finally obtain that the x00 has to be this, and then you iterate. By iterating, you obtain finally this equation, which gives you that, as in the formula I showed before, the psi I have to put have to be a dm root of unity, which was the psi I put in the original formula. And then we have an epimorphism to the diagonal part from this z over dmz, and the kernel, you compute it, is the d root of unity. So the diagonal part is a cyclic group of order m, the number I showed you before. So maybe not all these computations can be followed this quickly, but believe me, it's straightforward computations. Just go and check with math from, I don't know, first year, no, not first year university, like way before. And so, like this, we can finish the computation of the missing automorphism group of the Klein hypersurface. And this we did it in a much larger context. So the paper has a name that has nothing to do with this. So we were doing something different, but I really wanted to concentrate only on hypersurfaces. So if I'm not mistaken, this is where I end. Thank you very much. Thank you.